All right, so we had this big expression here for concentration, and it was basically built from two elements. We started with those two elements in the light gray on the right, where we had moles of something divided by volume. The moles of something we ended up expressing in terms of conversion XA, which is what ended up being on the numerator. Not an awful expression. The volume tended to be a little bit more complicated because volume can change. So we used the ideal gas law to come up with that expression on the bottom. If you don't want to use the ideal gas law, which you should use it for this class because it results in that, that's fine. The only other thing that you have to do is add the Z factor on there, the compressibility factor. So instead of T over T naught and P over P naught, you'll have another one like Z over Z naught, and you can get those two Z's from whatever equation of state you want to use. We're never going to do that in here. We're always just going to use the ideal gas law because that's kind of bad enough, right? We don't need to add anything more to that. So in your notes, you should have this example. There's nothing new here. It's just so that I can start writing again. But we were looking at this 2a plus b goes to 3c. And all I wanted to do with this example was finish up what these expressions for c look like over in the third column. That tends to be where you have to go when you start the next part of the class when we're dealing with these reaction rates, because very often they're written in terms of concentration. Yeah? How do you get it? So in this particular case, we were told that there's a 50-50 mixture of A and B. So the mole fraction of A is 0.5 and the mole fraction of B is 0.5 initially.
So YA equal to 0.5 and YA.
Correct. Well, YA 0, the initial concentration. Yeah. So the two elements that we had left off here was the theta column. So we had originally defined theta as the moles of any species I initial. Oops, I actually didn't define these correctly. The moles of I initial over the moles of A initial, which is the same as the concentration of I initial over the concentration of A initial, because they're both, you can divide the top and the bottom by the volume initial, and you end up getting the same thing. So that particular column is usually pretty easy. So the theta of A, if you ever need theta A, in this particular case, it's 37 over 37. Which is just 1. Theta B is also 1, because that's 37 over 37, so that is this one divided by that one. And theta C is also pretty easy in this case, that's 0, because that's 0 over 37. So as you get more comfortable with theta, you may not need an entire column for theta, which is fine. You don't have to have a column for theta. It's that CI column where most of the effort comes in this particular stoichiometric table. By the way, we call all of these stoichiometric tables. We had one in terms of n and squiggle, we had one in terms of n and x, and now we've got one in terms of c and x. There's no distinction in names for any of those. They're all stoichiometric tables. They're used interchangeably. So when it comes time to get C sub I, an expression for C sub I, the first thing you should do is go back to this particular expression up on the top and figure out what's happening in the denominator. Figure out whether or not V is constant. If V is constant, then that whole term on the bottom is just equal to V0. There's nothing else there that you have to worry about. But you should check each one of those terms carefully and find out whether or not they either go to 0 or 1. So that you can decide whether or not you need to get rid of the denominator or keep the denominator. So in our particular example, we were told that temperature and pressure are constant, which is nice because then if we flip back over to this one, that means this ratio is equal to 1 because the initial temperature and the final temperature are the same. It's isothermal. We were also told that it's isobaric, so this is also equal to 1. Great. Simplifies it a little bit. We still need to work on the 1 plus YA naught times delta times XA. Typically, YA naught will never be equal to 0. Otherwise, you don't have any of your reactant in there to begin with. And in general, XA will also not be 0 because otherwise you're not converting anything. So the one to look at on that particular term is delta, which I've already highlighted here. If we look at delta for our particular example, so our stoichiometry was 2a, 1b, and 3c, we just have to calculate delta based on that stoichiometry. There's no shortcut to doing that. You just plug those numbers into that expression. So if we plug those numbers in, I usually start with products. You don't have to start with the products, but by convention, you will often see delta written this way, where it's in terms of products. So I will write it that way. For our product C, we have a 3 over, I think it was a 2, right? Yeah, I just forgot that. So 3 is the stoichiometric coefficient of C, 2 is the stoichiometric coefficient of A, and then we subtract off the other ones. So we've got 1 for the stoichiometric coefficient of B over 2, because 2 is the one for A, and then it always ends up being minus 1 at the end, because that's the stoichiometric coefficient of A divided by the stoichiometric coefficient of A. Anybody know what that is? 0. Zeros are usually pretty easy ones to catch without having to do the actual delta fraction that we've got here. The easiest way to do that, to see quickly whether it's 0 or not, is I know 2 plus 1 is equal to 3, and I've got a 3 on the other side, so delta has to be 0. In general, I'm taking 3 molecules on the initial state, and I end up with 3 molecules in the final state, so delta is 0. If you can't do that check really quickly in your head, then I almost always end up calculating delta anyway, because I make mistakes pretty commonly when I'm trying to do that. But if you just look at the expression and you realize I start off with the same number of molecules as I end up with, then delta will be 0, which is nice. So as a result, we've got a 0 over here, which means this entire term is equal to 1. Because we've got a YA naught times an XA times a delta. The delta is 0. We're still left with the 1, which means the entire bottom of this expression is just equal to V0. Great. Volume is constant. That will not always be the case. If volume is not constant, you just have to come back here and use this particular expression. Because volume is constant, we've got a little bit of a simplification here, which I think I had mentioned last class. We can leave this as CA0. Actually, you can write that regardless of whether volume is constant. But that's all of the expression that we're dealing with. When we fill in these CI terms, they're all going to look like CA0 times theta I minus the stoichiometric coefficient of I over the stoichiometric coefficient of A times XA. Right? Every element in that last column of the table we're about to fill out is going to simplify to what I've written in green up there because volume is constant. The only shorter way to do that is if somebody tells you volume is constant. If somebody tells you volume is constant, it always ends up looking like this one. So this is when V is constant. The reason for that is because that expression, the big nasty expression that we have on the bottom there, was assuming that volume was not constant. We did that ratio of 2 ideal gas laws. So if volume happens to be constant, that term will always end up simplifying in exactly that way. That we've seen there. Even if other things are changing. If somebody just flat out states that volume is constant, skip to the green on the top. So if I use that green expression on the next page, over here, we've got the concentration of A is equal to Ca naught times theta, which is 1, minus the stoichiometric coefficients of the 2 species, which ends up being minus 1 XA. The signs there get a little bit wacky, so be careful with your signs. In general, you'll always have a negative in front of the X if the thing is a reactant and a positive in front of the X if it's a product. That's a good rule of thumb to keep in mind. C sub B will look pretty similar. It's still CA0. The theta term that we had here was 1, which we determined from the last one. And now we have to come up with the ratio of stoichiometric coefficients. So the stoichiometric coefficient of B, according to that expression, is 1. The stoichiometric coefficient of A was 2. And if you work out those negative signs, it ends up being minus. And the last one, C sub C, is going to be equal to CA0. The theta for C sub C we already found was 0. It's 0 because we didn't start with any of C. And if you do that balance, or well, not that balance, if you look at the way the stoichiometry works out, we've got a 3/2 over there. And the signs work out so that this is plus. So 3/2 times XA. That's a pretty standard format. You're going to see various patterns like that pretty often. The only major changes that we end up getting are sometimes the thetas aren't 1, they're different numbers. And obviously the stoichiometry is going to change. By far the biggest mistake that we see is either CA naught gets changed. So it's very easy to write, okay, CA is CA naught times something. CB is CB naught times something. CC is C naught times something. But it's always CA naught for all of those expressions because of the way that we're using theta over there. That's a very common one. And then the other common one is messing up the stoichiometry here. I worked an example this morning and messed up the stoichiometry. It's an easy mistake to make. You just have to be rather, what's the word, vigilant when you're doing the stoichiometry. There's a question over there?
Yeah, one more time. Why do you do 1 minus XA versus just 3/2 minus XA? What is that expression?
The 1 minus XA for CA? Yeah, so for CA, what we've got here, actually, I'll just flip back one page. The stoichiometry, so this is 1 for that particular example because, well, it's always 1 for species A. The stoichiometric coefficient of A itself is -2. So that's what's on the top. It's always divided by the stoichiometric coefficient of A, which happens to be -2 again. So we have another -2 here. So -2 over -2 is +1, but there's a negative sign sitting out in front, so we end up with -1. The one for A, if you ever find yourself getting anything other than 1 minus XA here, look real hard at that one. Because the one for which you're writing everything else in terms of, so the species A, I don't think I've ever seen anything other than 1 minus XA right there, because everything's been defined in terms of XA. So that's the only one that's really predictable. If you get anything other than that for CA, look hard. There's something funny there. You could have that big term in the denominator for volume, but in terms of concentration on the numerator, it should almost always look like that. So this is a typical stoichiometric table. The reason that this comes up so often is we need these expressions for CA, CB, and CC when we're writing rate laws, which is what we're going to talk about today. The easiest way to come up with what those are is to just do the stoichiometric table like this. They're going to look like that. So in terms of rate law, we do have to make one change. So we are now introducing the very last thing. No, it's not really last. Everything that we do from this point on is looking at the impacts of what we're about to write. The rest of the class is looking at how does this change things. So the overall material balance that we had was the change of moles in time. I'm going to use moles and not mass, but you could get the same thing from mass. Was in minus out plus change. Since we're operating at, not steady state, operating in a batch reactor, we don't have any flows going in or out. We will see how those terms impact things later. Previously, we had learned that this change term was the one that had this squiggle term. Right? All of our changes were proportional to the extent of reaction. The extent of reaction is fine, but as we've seen in every problem we've worked up until now, it didn't have anything to do with time. We couldn't relate it to anything with time, at least not in a general way. So the change term that we have, oh, get it? Remember the new term the other day was all news? The change term is where the change happens. The change term is what we're going to modify here. This will always look like R sub I times V. Every single time, it always looks like R sub I times V. And so that will end up being equal to the moles of I, or sorry, the rate of change of the moles of I with respect to time. So this ends up being the expression that we end up using. We're going to modify that expression in half a dozen different ways for various reactors, for various variables that some work better than the other in various situations. But that's the core expression that we're going to deal with. This R sub I, can you guys see the purple, or would you rather a different color? Is it okay? Everybody up in the back, you can see it? Cool. So R sub I is defined as the rate of generation or consumption. It does not matter. We pack both generation and consumption into that single term, R sub I, of species I per unit volume. And per unit time. That's not an either or, it's both. As a result, the units of R sub I end up looking like moles of I divided by something like time, whatever that time term happens to be, times a volume. So a typical unit for R sub I is moles of I per liter per second, something like that. It is moles of I generated or consumed. We just usually don't denote the difference between those two because both of those are happening almost all the time with a reversible reaction. So we're going to look at R sub I because there's a couple of different terms that go into it. There are a few variations on this expression that we can use. This one is the general one. What I mean by general is that we usually use this if V is not constant. If V is not constant, you're kind of stuck with this particular expression because chances are V is going to be a function of the moles of I, and you're going to have to deal with it somehow. Or at the very least, you'll have to start there in order to deal with it. If V is constant, though, we have a slight simplification to it. So if V is constant, we can use the expression that we had defined before as the moles of I is equal to the concentration of I times volume. We had defined it the other way around, concentration is moles per volume, but I just rearranged it here. If we substitute Ci times V for Ni in the previous expression, we can factor that volume out because it's constant, so we don't need to leave it inside there. And the end result is that the change in concentration of I with respect to time is equal to R sub I. That's another very common form that you're going to come across. The only advantage here is there's no volume term that's explicitly there, but again, it only holds if V is constant. If V is not constant, go back to the other one. If we end up solving that, it typically involves integrals that go from initially a large number to a somewhat smaller number. There's a more convenient term to use for this, which is conversion, simply because conversion always goes from 0 to something. And so the bounds of those integrals are usually simplified a little bit. If you ever have to solve them by hand, the expressions that you have at the end are a little bit easier. The simplification for that is usually in terms of a particular species. So if you write specifically that, what was it? X sub A is equal to 1 minus C sub A over CA naught. Remember, this is at V is constant. That's the same XA that we had defined previously. Moles initial minus moles final over moles initial. Same thing here, we just kind of rearranged it a little bit. Then instead of writing dCi for any species I, although that does hold for any species I, you can write that expression specifically for dCa. And if you do that, it simplifies a little bit to dxa dt is equal to minus Ra divided by Ca0. So the only way that I got that was to take this expression and plug it in up here, specifically for species A. Right? You'll notice I dropped the i's here. I'm talking just about species A. We usually don't write that for any of the other species. It's always just for species A, whichever one happens to be the most useful species that we're dealing with. And so this is, again, V is constant. Yeah.
So when you derive the expression for ni is equal to CIV, you said that it's usually for dilute samples.
No, that was, so Ni is equal to Ci times V is a general definition. It's not a derivation.
But when you do the dCi dt equals Ri,
Mm-hmm.
for V equals constant, and that's for dilute samples, right?
Not necessarily. It could be for dilute samples if it's in a liquid phase, but it could also be a gas phase reaction that just happens to occur in a constant volume container.
Yeah, I think, so my question is more in the liquid phase. Why is it important to say that it's a dilute sample?
Because when you do when something undergoes a reaction, usually the molar volume of the reactant and the product are not the same. So even though the liquid is incompressible, the molecules themselves can take up more space, and that can tend to change the volume. So if the molar volume of the two species is not completely identical, then you do have to make the assumption that they're so small, or the changes are so small, that the volume is essentially constant. Molar volumes for liquids tend to be pretty close, but it gets weird, for example, if you're in biology, because those molecules are really big and their molar volumes may not be very close to each other. So there, a dilute assumption helps you out a lot. The easiest way, by the way, to get a reactor to have constant volume is put it in a rigid container. If it's a gas phase and you put it in a rigid container, the volume is constant. Which is not unusual. There are reactors, they're called bomb calorimeters. I don't know who came up with the word bomb, but they're very common for investigating properties of fluids. So any three of these, they all essentially mean the same thing. They're all material balances. You can either talk about it in terms of conversion, which is this one down here. Remember, it's always written in terms of species A. You can write anything in terms of concentration changes as long as the volume is constant. If it's not constant, then you end up having to go back to this general one, which is the moles of I changing as a function of time. You can use any three of those provided the constraints are satisfied. They will all give you exactly the same answer. What do these problems typically look like? These problems look like this. Suppose we had A goes to B, and to make our lives easy, somebody said it's constant volume. And we're told that the reaction rate R sub A, I'm leaving a little bit of space here because I'm going to add a negative sign. Whenever we're talking about species A, it's almost uniformly one of the reactants. It's very rare that we choose a product as species A. And so whenever you see a reaction rate written this way, you will often see it as R sub A with a minus sign in front of it. The reason for that is because A is being consumed. So the rate of reaction of A is usually negative. It's going down. The concentration of A is going down. Sometimes the negative will be on the other side. The more confusing times is somebody will just say R is equal to K times C, and then you have to read carefully and figure out from the context which R they're talking about. You'll almost always see it like this with a negative sign in front of it. And so we can plug that into dCA dt is equal to RA, which is then equal to minus KCA. All of these have to have some kind of an initial condition. So for example, CA of T is equal to 0 is equal to CA 0. Again, the stoichiometric table will come in handy right here because CA 0 is probably in your stoich table somewhere. If you rearrange this and integrate, you can end up with DLNCA is equal to the integral of minus KT, K dt. The integral limits here are whatever you started with. So initially at time 0, you had CA 0, and at some new time t, you had some new CA, which is whatever, CA. And if you work out that integral, you end up with CA as a function of time is equal to CA naught times the exponential of minus kt. That's just about the simplest reaction that we can come up with. It could be a little bit simpler if when you wrote RA, you just wrote it's equal to K, a constant, which, by the way, K is a constant here. It's not a function of anything, it's just a constant. You can plot things, not surprisingly. And you'll be asked to plot quite a few things on your homework. So that would look something like this decaying with a function of time, where that particular point up here looks like CA naught. In fact, it's exactly equal to CA naught. You could rederive the entire expression in terms of x, or you could substitute in the expression for x, and you'll end up with something similar, which is that xa as a function of t will end up being equal to 1 minus the exponential of kt. So you can arrive at that expression in one of two ways. You can either use the definition of A on the final form of CA that we've got down here, or you can go back and change the original differential equation you solved over to the XA one. You'll end up with the same one in either case. One of the advantages of the X term is that whenever I plot it on a scale of anything, whether it's time or space, as we'll learn in a minute, it'll always go up, and it's always capped at 1. The conversion won't exceed 1. There are rare cases where it can look like conversion has exceeded 1. Usually it's just because you didn't follow some of the numbers around carefully. But it's always capped at 1. And so that makes it kind of a convenient thing to plot, because at least you have some intuition about how big it can be. It's the equivalent of saying CA is capped at a minimum of 0, right? We can't have a negative concentration. But for whatever reason, that tends to be a more convenient method. That's about, that's about as easy as it gets for this particular one. Why do I need the stoichiometric table? The only time that I really need the stoichiometric table is if I didn't want to write it like this. If I wanted to write it as dxa over dt is equal to minus RA over K. Or no, not minus RA over K, CA naught. This is going to end up looking like minus K, plus K, times CA over CA naught. But CA, as we saw from that stoichiometric table, is itself a function of XA. The only way that you know that that's a function of XA is to do the stoichiometric table, or the only way to know what that function of A is. And so this would end up looking like K times 1 minus XA. If you plug in that expression that we had previously for CA, it was CA naught times 1 minus XA, and we end up getting that. That's why we need the stoichiometric table, because often we want to solve that particular differential in terms of conversion rather than the differential in terms of concentration or moles. So either one of those end up with the same result. Keep in mind, if you ever do the one for conversion, the initial x0 is always 0. The initial conversion, so your initial condition for that differential is always 0. There's, several dozen different ways that we can come up with this particular expression. We call that expression, whenever you see RA is equal to a function of like a constant and some concentrations, we call that a rate law. So the name of this term is a rate law. And the question becomes, how do we figure out what that rate law is? There's two ways. One, assume it's really simple. Two, go into a lab and measure it. Even if you do option one, which is assume it's really simple, you still have to go into a lab and measure it. At the end of the day, we have no way at the moment to theoretically predict what that rate law ought to be. We can get really close. There's some efforts that we can go into quantum mechanics. If anybody's going to take a PChem class, you can find out how we can get really close with PChem. But we can't get all the way there, and it's usually accurate only to within a certain fudge factor that has to be verified in the lab. So at the end of the day, the rate laws are always experimentally determined. Any rate law that you're given will probably be either simplified or you'll get the actual one from experiment like you have on the third homework. You have a real one. So how to get Ri? There's generally only two ways to do this that I had just mentioned. There's a third way that's kind of a shifty way, but you need one of the other two in order to do it. The first way is to assume that the reaction is what's called elementary. If you assume a reaction is elementary, then the rate law that you end up writing, for example, R sub A, looks like this. It always looks like a constant K. We always use the constant K. Times the product of the concentrations of I raised to their absolute value of stoichiometric coefficients, but only for the reactants. Written in its general form like that, that does not look like the world's easiest expression to use. It ends up being really easy. So, for example, if you have the reaction A goes to B, and you assume that this is elementary, then R sub A minus R sub A is equal to K times Ca. Right? That's not that hard. A on the left-hand side has a stoichiometric coefficient of 1. It's the only thing on the left-hand side, so Ra is equal to Kca. If the reaction is elementary. If it's something else, like another common one is A plus B goes to C. If you assume that that one is elementary, then this is R is equal to K times Ca times Cb. Right? Those are elementary rate laws. They're about as simple as we can get. They're not bad. Most of the time they're fairly accurate. But again, they have to be verified experimentally. There's one modification to that particular rate. Sometimes you will see it in terms of concentration. Very often for gases only, which actually I think I'll write this in another color, minus Ra, specifically for gases, looks very similar. It's still K times the product of a bunch of terms, but the terms that we have here are partial pressures. So raised to their stoichiometric coefficients. Again, just for the reactants. That pops up very often in gases because partial pressures are easy to work with. In fact, they're often easier to work with than Ca. So for example, if I had this same expression, A plus B goes to C, and I wanted to write that elementary rate law in terms of partial pressures, this would look like K times PA, PB, where PA and PB are the partial pressures of A and B. That does not mean that those two Ks are the same. So even though I wrote it in two different ways right here, those two are not the same. We just use the symbol K all the time. If you ever have, I can't think of a reason why you would need to convert back and forth between the two, but if you ever had to do it, you'd have to throw some unit conversions in there because they are not the same thing. But you will always see them written as just the variable K. So this is case one. If the reaction's elementary, we can do this. The top one, the one in the white, the Ra is K times the product of concentrations. That's good for anything. Solid, liquid, gas, doesn't matter. We can do that one. If you just happen to have a gas, sometimes you'll see it written this way. It doesn't really change the approach very much. Yeah?
If we also consider between gasities and the activity coefficients, would that still be considered elementary?
Yes. So that's a good question. No assumptions that you have about whether the solution is real or ideal or follows one particular gamma or another gamma or one phi or another phi ever changes anything that's over here. Yeah? That's what it means. So if it's elementary, it means it follows this rate law. That's the definition of it. Yes. So you would not be able to write an elementary rate law for an arbitrary reaction. If you tried to do it, you would end up with that product term that I have there, where you've just kind of got general symbols, C sub I and nu sub I. But there's no one single reaction that works for everything. So that's an elementary rate law. There's a little note about an elementary rate law. Most of the time, these things end up looking like R sub I is equal to, sorry, not R sub I, A, is equal to something like C sub A raised to the x power and C sub B raised to the y power, right, where x and y are whatever those stoichiometric coefficients happen to be. The order of this reaction is the sum of x and y. So if somebody tells you this reaction is second order, that means the sum of the exponents up there is whatever that order happens to be. So if it's, for example, order 2, that means x plus y has to be equal to 2. It doesn't say anything about the individual values of x and y. It just says that the sum of those is that particular order. You can also write this as order x in A and order y in B. So that's nothing but nomenclature. So occasionally you will see these things written in that particular way. It doesn't really impact anything that you would do in terms of solving the problem. It's just you see that terminology pretty frequently, so you should be aware of what it is. There's not really anything we can test you on that. It's just summing up those two exponents. The other option, let's say the reaction is not elementary, like a fair amount of reactions happen to be. The other option, if it's not elementary, it must be non-elementary. Elementary. Engineers are not the most clever people when it comes to names. If it's a non-elementary reaction, this one has to be given to you. You can't guess the form of a non-elementary reaction. It means somebody figured it out by experiment. Somebody went out and said, I've got a couple of different rate laws. I'm going to do the actual experiment, see which one matches best, and that's the rate law. And so you can end up with non-elementary rate laws. So as an example, if you had the general reaction A goes to B, we already saw what the elementary rate law was. That was on the previous slide. But there's no reason that that reaction rate has to follow that elementary rate law. It could equally be something like minus RA is equal to K times CA raised to the 1/2. Right? That's a non-elementary rate law. If it were elementary, it'd just be KCA. But if somebody went out and actually measured it and found out, well, it's not quite elementary, that's fine. Use the version that they've got here. They also don't have to look anything like that. If you have something like RA is equal to, this is a neat one, V max, the biologists define reaction velocities, which I think is kind of neat. I don't normally interpret reactions in terms of velocity. But you can have something weird like this, which has a bunch of terms we've never seen before. Vmax is a velocity, CS is the concentration of a substrate, which isn't species A, and then Km is some other equilibrium constant that we've never seen before. That's totally fine as long as somebody gave you all those numbers or expressions for them. It's just another example of something that's a typical non-elementary rate law. The approach doesn't change. You still put it into the same material balance. The only change is the math probably gets a little bit uglier if it's a non-elementary rate law. But at any rate, those have to be given to you. By the way, the order of this one, would be said to be equal to 1/2. The order of the one underneath, there is no order of that. You just wouldn't use that terminology to describe that rate law. So those are the only two options, right? We've divided the entire world of reactions into either elementary ones or non-elementary ones. If they're elementary, you know how to write the rate law. You just base it off of the stoichiometry using that underlined equation there. If it's non-elementary, life is a little bit easier in the sense that it has to be given to you. You have to look it up or something like that. The third case that I said was kind of a cop-out, it uses the first two cases. Notice everything that we've written here is in terms of R sub A. right? There's this one, it's R sub A. If we go back here, every one of these R sub A's that I wrote over here is R sub A. What if you need the concentration of something else? You use stoichiometry to relate all of those. So 3, I hesitate to really even call it 3. This is if you're dealing with something other than A. Most of the time you'll see it written in terms of A, but if you need one of the rates in terms of something other than A, like you want to know the generation of B or something like that, the general relationship that relates any two rate laws is that the rate divided by the stoichiometric coefficient for one species is equal to the rate for the other species divided by its stoichiometric coefficient. So that's essentially stoichiometry. If I destroy one molecule of A and the reaction is A go to B, I must be getting one molecule of B. So often you'll see this written as something like R sub A over minus A is R sub B over minus B, R sub C over C, and R sub D over D. Right, if you wanted to write that for that generic reaction that we have, A plus B goes to C plus D, that's what that expression ends up looking like. But the general one is the one up top. So it's not really, it's not going to give you another rate law, right? Somebody has to, you either need an elementary or non-elementary rate law before this stoichiometry becomes useful. And it doesn't come up all that often. Most of the time we're just interested in A. It does become more important when we get to multiple reactions. So not next week, but the following week, we're going to need to use this a lot. Until we get to that point, you probably won't come up with this, and I will remind you of it when we get to multiple reactions, because it's important there. All right, I want to make one, let's see, we've got 5 minutes. Perfect. I want to talk a little bit about that K parameter. Do I need to do any of those notes? No. I guess just one aside that I have here. So I said the numerical values of those Ks are not equal. Are the units of those Ks equal? Usually not, right? Unless the order of the reaction happens to be exactly the same, Ks will not be equal. So be very careful whenever you're writing these things down. The units on R sub A are fixed. We defined those units towards the beginning of the lecture. Those never change. They're always moles per, amount per volume per time. That's always R. The units on K, though, just adjust in order to make R come out to have the right units. The units of C sub A and C sub B vary. They're always amount per volume. So whatever mixture you have over there on the right has to end up giving you the correct units of RA. So there's no single unit for K. It varies with the reaction that you've got. Which is why when you look in your homework, you'll see lots of different units for K. It's so that the units work out. That constant K follows what's called an Arrhenius form. Arrhenius form, which means the following. You will see K sometimes written as K is equal to A times the exponential of minus E sub A over RT. So the E sub A here, you've probably seen that term before. This is called the activation energy. The A that's here doesn't really have a particularly clever name. Sometimes it's called the pre-exponential factor, right? Because it comes before an exponent. I didn't make that, I know, right? That's the name that they came up with. Other times you will also see it called the frequency factor. It's the same thing. They're used interchangeably. And then the K over here on the side is always called the rate constant. This is where occasionally, if you're going to get interested in that quantum mechanic derivation for something like K from one of your physical chemistry classes, that's where you'll spend most of your time, is figuring out what that pre-exponential factor is. We have some pretty decent ways to go about that, all of which are basically a class unto themselves. But what this expression is saying is two things, and this is about all we'll have time for. However, this is enough to get started on almost all of your homeworks. If you look at any reaction coordinate versus the potential energy of the system, you've probably seen a plot that looks like this before. The difference between where you started and the highest you need to get to is E sub A. It's called the energy barrier. You have to supply a certain amount of energy in order to get two molecules to react. That's quantified by the value of E sub A. The other one, the difference between the initial and the final, that's delta H. We've already seen that one before. That's the enthalpy of reaction. Because this thing follows an Arrhenius form, or actually it's the other way around, because the plot I'm about to make is true, it follows an Arrhenius form. If you look at the distribution of energy between molecules, so if you call this one, I'm going to call it F, the fraction of molecules that have a particular energy. If the temperature is low, this tends to look something like that. And so the activation energy is just sitting out here somewhere like this. And the only collisions that will result in some kind of a reaction are the ones with E greater than activation energy. So it's only the fraction of molecules that are out here. If you integrated the area under that curve, it's only those molecules that are going to be the ones that react. So that's at a low temperature. If you increase the temperature, this curve shifts a little bit. It gets a little bit shorter, but it also stretches out. And so now the fraction of molecules that collide with enough energy to react is that area, which is bigger. This is why we almost always want to increase temperature in order to speed up the rate of a reaction. That is one trend that never changes. If you increase temperature, you always increase the rate of reaction. Whether or not that's a good thing or a bad thing depends on other parameters that we'll get to when we talk about the energy balance for the system, for non-isothermal systems. But if you just want to deal with rate in terms of K, if T goes up, you always get that K goes up. That is always true. It will not change at any time. The rate always goes up if you increase temperature. So that should be enough actually to get a decent way in your homework. Please keep in mind, we're about to hit the part of the class that requires a lot of MATLAB. If you're rusty on MATLAB, there's a couple of resources that are on the Triton Ed site that'll help you get moving again. And if you've never solved anything in ODE 4.5, there's resources for that too. We're going to do a couple examples of ODE 4.5 in the class, but very quickly it'll become a standard tool you need for the homeworks. So please brush up on that if you're not familiar with it, and I will see you tomorrow.